So let's consider a standard irreversible process. That is the free expansion. So we have gas in one half of a volume with two halves separated by a stopcock. When we open the stopcock, this gas can freely flow from the left-hand side into the right-hand side and will flow until it's evenly distributed across both sides. It will never, no matter how long you wait, flow back in and have all of the gas in one side. So let's try and understand what the change in entropy is in this process. It turns out that the macroscopic definition of entropy, or at least of the change in entropy, is that the change in entropy, the final entropy minus the initial entropy, is defined to be the integral from the initial state to the final state of a little bit of heat, dq, over the temperature. So all we have to do is integrate the amount of heat divided by the temperature from the initial state to the final state. But we do have a little problem. Namely, there is no heat that's transferred. And you might think from that that means there's no increase in entropy. Why is there no heat? Well, this is entirely insulated. No heat comes in or out. The gas just spreads out. But it turns out that doesn't mean we have a zero change in entropy, because this integral is really only good for a reversible process where we can define temperature and heat very carefully. In the process we know the initial state and we know the final state, but in between there is no well-defined pressure and volume. As a result, we can't do a well-defined heat or even a well-defined temperature. There's no well-defined temperature over here in the vacuum. So we can't use this law directly. But there is a very useful loophole or caveat. Namely, we said that entropy was a state variable. In other words, I don't have to do this integral according to this process. If I were integrating just heat, I would have to know the process, and the answer would depend on the process I used. But I'm not integrating just heat. I'm integrating entropy. Entropy is a state variable, so I can use any process I like. That's this statement here. Assuming entropy is a state property, we can find the entropy change for an irreversible process occurring in a closed system by replacing that process with any reversible process that connects the same initial and final states. We can then calculate the entropy change for this reversible process. The change in entropy for an irreversible process connecting the same two states would be the same. So let's think of a reversible process that would go from this initial state to this final state. That's fairly simple. We start with the initial amount of gas. The small one is the initial amount. And the pressure is maintained by lead shot on top. The cylinder is mostly insulated, but there's a thermal reservoir on the bottom that maintains a constant temperature. Heat can flow in or out from that reservoir to maintain the temperature in here. Then as I very slowly reduce the pressure by taking the lead shot out, heat will flow in to do the work that lifts the lead shot up. So we will have an isothermal, constant temperature change. We will have a well-defined temperature at all times. We'll be able to know the heat, and we'll be able to integrate our equation for entropy.